Now I left myself plenty of room to clutter up this diagram or this board, and I've done that with a different colored chalk so you can still see the original structure. But I want to remind you of a few things that you should recognize, but things that you might need to review if you really want to make use of this. Okay, for power functions, we graph in terms of a y factor, and we know what that means, but just to be sure, the y factor is the factor by which the value of the function, the y value, changes when we double the x value. Okay, exponential functions are characterized by doubling displacement, a displacement in one direction or another, some distance, on the x-axis, for which the y value doubles. The y value at one point is double the, well, okay, to get the y value after a doubling displacement, you take the y value before and double it. And you keep doing that and you get an exponential graph. And then for sine functions, as you know, everybody did this on the final, I'll just remind you of the reference circle. We have the reference circle. We divided it, the first quadrant, up by bisecting the angle between the x and the y axis. And then by bisecting that angle and that angle. Okay, by bisecting the two angles that we got when we bisected the angle between the x and y axes. So that gave us 4 points on the reference circle. We projected each of those points to the y axis. And then we graphed in units of our quartered angle, okay? But by bisecting twice, we cut the angle between the x and the y axis into 4 parts. So we'd have 0 here, 1 here, another angle would take us up to here, another to here, another to here. So this would be 4 units of our quadrisected angle, okay? And we graph the y-coordinate versus that angle. And that gave us the graph of the sine function. We extended that graph by symmetry all the way around the circle and obtained a complete cycle of the sine function. A well-constructed sine wave. Okay, and when we talk about geometric and algebraic combinations, what are we talking about? We're talking about constant multiples, sums, products. I got room to insert at least the abbreviated word constant. Constant multiples, sums, products, composites. We can geometrically construct any of these things given the original graph or the graphs of the original functions. And we can also obtain the algebraic formulation. With graphs and slope graphs, we learn to construct slope graphs. That's something nobody really had any problem doing, although it's somewhat tricky to do it with a lot of accuracy. We pursued a couple of big deal numbers. One, the number that the y factor for a power function whose slope graph is a straight line, and the base of the exponential function for which, or the doubling displacement actually for an exponential function, which is equivalent to the base, for which the slope of the graph of the tangent line is equal to the value of the function at the y-intercept. Okay, these are both really big deal numbers, often defined otherwise, but in terms of the geometric picture, these definitions are appropriate, and understanding how these definitions relate to the standard definitions significantly deepens your understanding of mathematics, the elementary functions, and the functions, the individual functions. We looked at curvature and concavity when we looked at the maximum curvature, how the maximum curvature of a power function is related to the y factor for that function. And of course, y factors can be related to the power of the power function. I wanted to say exponent, but since everybody confuses exponential and power functions, even in the media, I didn't want to use that word. Okay, the power of the power function and the y factor, as we know, are related in a fairly simple way. As far as inverses, and I meant to mention that earlier, should have been mentioned along with this, the combinations and so forth. Inverse of a function, the graph is constructed easily by simply reflecting the function through the line y equals x. So that should be familiar to everybody. The applications, we observed pendulums, we observed water flowing from a hole in a uniform cylinder, how the depth changed with time and how the horizontal range of that stream changed with time, and how the temperature of an object placed in a room approaches room temperature. These being examples of power function, exponential function. And water flow is a power function, but with some transformations involved. It turns out that that is the depth of the water is a quadratic function of time, and the horizontal range is a linear function of time. And that's a profound relationship. We didn't get to go into all the details of that relationship, which are not particularly difficult. But we did learn in observing systems how they can be modeled by elementary functions. And then interpretations. The most important thing we can do as far as interpretation at the beginning level at least is to understand what the coordinates of a point on the graph mean and what that means algebraically as well as geometrically, and then what the rise means, again algebraically and geometrically, what the run means, what the slope means, and what the units of these quantities mean and what they tell you about all the other meanings. So that's kind of an overview of the most important central core of the course. Now we also mentioned matrices and sequences of series, transition matrices, trapezoidal graphs, etc. So we'll see how all that relates. But this should serve as a refresher, a reminder of the central ideas that we developed in the course.